In this lecture, we explore the twin paradox, which shows that time travel into someone else's future is possible according to special relativity. In our thought experiment, a traveler visits the star Vega, which is shown in this photo. We will use the ideas of time dilation and length contraction developed in the previous two lectures. Here's the setup. Imagine two twins, Al and Gracie. Each are 20 years old. Gracie is the adventurous one. She sets off to go on a trip to the star Vega, which is 25 light years away. Her spaceship travels at 98% the speed of light during the trip. Once she arrives, she turns around and immediately returns to Earth at the same speed. The question is, how old will Al and Gracie be when she returns to Earth? Before we get started, we should define what we mean by the term light year. A light year is the distance light travels in 1 year. Thus, we can calculate how far a light year is by simply taking the speed of light and multiplying it by a year. It turns out that a light year is a little less than 6 trillion miles. So to solve the problem, let's first make a sketch. First, we'll draw the Earth with Al and Gracie. Next, we'll draw Vega that is 25 light years away. So again, Al and Gracie start off on Earth, and they're originally the same age, 20 years old. Then Gracie gets aboard a spaceship and travels to Vega at 98% the speed of light. Let's first look at the trip from our perspective on Earth. So in the Earth frame, or in Al's frame, it takes Gracie a time dt equals L0 over v, or 25 light years over 0.98 c to reach Vega. The c's cancel, and we see it takes 25.5 years for the trip. The total time for the round trip will just be twice this. Because we're assuming that Al and Gracie are both 20 years old when they start the trip, Al will be 20 plus 51, or 71 years old when they reunite. Now let's look at the trip from Gracie's point of view. Instead of Gracie traveling at 98% of the speed of light through space to Vega, Gracie sees the Earth and Vega moving to the left as she is stationary in her own reference frame. We know that Al and Gracie are in relative motion, so we can use the time dilation equation dt equals gamma dt naught. The first question is, who measures the proper time? Al is at rest with respect to both Earth and Vega, but Gracie is the one who actually travels to Vega. So to answer this question, it helps if we define two events. Event A will be the moment in time and space that Gracie leaves the Earth. Event B will be the point in time and space when Gracie arrives at Vega. If we think about this from Al's perspective, we know that Gracie starts out on the Earth, travels through space to Vega. And so these two events, A and B, happen in two different locations in Al's frame of reference. We could write event A being on the Earth and event B being at Vega. However, in Gracie's frame of reference, both events occur at the same location in her frame of reference. They both occur at the position of her spaceship. So A and B are at the same position. Now what happens is that the Earth and Vega are moving relative to her spaceship. So event A happens here when Gracie is on the Earth, and now in Gracie's frame of reference, the Earth and Vega are sliding past her, and now event B, when she arrives at Vega, is still occurring at the same position in her coordinate system. So we're used to saying that the proper time occurs when the person is at rest with respect to the clock. But in this case, we don't have a physical clock, we simply have two events. And so a more general way of defining proper time is to say that the events must occur at the same location for the observer to measure the proper time between them. Let's say that again. The events must occur at the same location in space for the observer to measure the proper time between them. Thus, Gracie is the one that measures the proper time. So Gracie will measure delta T naught, and Al will measure delta T. The time dilation equation is delta T equals gamma T naught, where we calculate gamma as 1 over the square root of 1 minus v squared over c squared. This works out to be 5.025 in this case. Solving for delta T naught and plugging in delta T equals 25.5 years, which is the time measured by Al, and gamma equals 5.025, we find delta T naught is 5.07 years. So the total time for the round trip will be 2 times 5.07, which is 10.14 years. Because Gracie started the trip when she was 20, and the trip took her approximately 10 years, she'll be 30 years old when she reunites with her twin brother Al. So in summary, Al will be 71 years old when they reunite, and Gracie will be 30. Here's the paradox. Doesn't this violate the principle of relativity? When you see someone in relative motion, you think their clock runs slow, but they think your clock runs slow. Neither frame is special. But in this example, both twins agree that Al aged more than Gracie. The symmetry between the two observers is broken. What's the deal? You might pause the video for a moment to see if you can figure out a solution to this paradox. So the answer is, we actually already mentioned the answer. When Gracie blasts off from Earth, she must accelerate to get up to 98% the speed of light. When she arrives at Vega, she must either swing around Vega or slow to a stop and then blast off again to return home. In either case, she must accelerate. This breaks the symmetry between the two observers, since it means that Gracie is not in an inertial reference frame during the entire trip, while Al is in an inertial reference frame the whole time. When she accelerates, the laws of special relativity no longer work, and general relativity must be used. But it turns out that even though we aren't using general relativity in this question, our calculation is still a good approximation to the answer that you would find in the more general case. So as a follow-up question, we might ask, how can Gracie travel to Vega in only 5.07 years when it takes light 25 years to get there? Doesn't this mean that Gracie is traveling faster than the speed of light? We'll show that faster than light travel is impossible in a future lecture. Again, you might pause the video to see if you can answer this question. All right, are you ready? The answer is length contraction. From Gracie's perspective, the distance to Vega is given by the length contraction formula L equals L naught over gamma. But of course, we have the same question again. Who measures the proper length? Al or Gracie? The answer is that Al does because he is at rest with respect to both the Earth and Vega. He measures the distance between two objects, Earth and Vega, and both objects are assumed to be at rest relative to him. Thus, L naught is 25 light years, and we find that the length contracted distance that Gracie sees is 4.98 light years. So we see that it only takes light 4.98 years to travel from the Earth to Vega in Gracie's frame of reference. She makes the trip in 5.07 years, so it takes Gracie longer to travel to Vega than it does light in her reference frame. So therefore she is not traveling faster than the speed of light in her reference frame. Okay, the next lecture will be on another seeming paradox, the relativity of simultaneity.